Differentiators are circuits that will give you the derivative of a waveform. Just like before when we talked about integrators, that integrated waveforms, differentiators give you the derivative. And they are also circuits that you've already seen, just like integrators. Basically, anything you put in, you get out the derivative of the wave. So if you have a sine wave, again, you get a cosine wave. It's just shifted in the other direction when you get the derivative versus getting the integral. So both ways you get a cosine, but in one way it shifted one, and one way it shifted the other. So that doesn't make it so interesting. A triangle wave will actually give you a square wave because the slope of the line at any given point is the derivative. So what you'll end up getting is, if you've got a positive going slope, you get the slope of the line. However, because this is an inverting amp, you actually get a negative value, so you get an inverted square wave coming out. And a differentiator also works over a frequency range just like an integrator. So there is and there's a typo in this. I don't like that. An differentiator. Oh well, I'll fix that someday, not today. So like integrators, we're going to go through almost the exact same process. Actually, it is the exact same process we went through last time with integrators. And you'll see it comes out to be very, very similar. So this circuit is a differentiator and also a high-pass filter. It is the same circuit we used for high-pass filtering a couple of lectures ago, but the frequency range in which it gives you the derivative is different. So just like the other circuits that we did, we're going to use a different frequency range and get a different response out of the same circuit. So again, we're going to do an example. We've got a differentiator with actual numbers, and we already know how to find the break frequency and the high frequency gain of this circuit because we did that when we did active filters. So the break frequency is just 1 over 2 pi R1C, and we figured that out. Remember, it's always the physical connection of the resistor with the capacitor is what determines break frequencies in these circuits. So because R1 is connected to the capacitor, that's the one we use to determine the break frequency. And the gain as the frequency goes up high is R2 over R1. And remember, with filters, we actually use the magnitude. We don't worry about the fact that it's negative or positive. We just use the magnitude of the gain just because that's what we do. So we actually get approximately 10 dB. And actually, it's exactly 10 dB as the gain. So that's what happens at high frequencies. And we can, again, look at the Bode plot of this as if it's run through LT Spice, and it does what we think it does. It has a break frequency at 33.86 kilohertz, and I did actually measure that, so it's not just made up to look right, and a high frequency gain of 10 dB. And remember, it's cut off real short because the op amp is going to start making it go down again if we keep going in higher frequencies, so we just don't. So we can divide it up again. We can divide the right half and the left half of the graph, and on the right is what is being used as a high-pass filter. So if it's a high-pass filter, you use frequencies above the break frequency there, and anything below the break frequency will give you a value where derivation can occur. We have the same characteristics as far as gain goes in the derivative side. We can actually find the 0 dB point where the gain is 1. So that's kind of the dividing point between whether we get an increase in the single signal when it's being derivated or the negative of the signal. Or a smaller signal. So the 0 dB gain on this graph is actually really, really close to the break frequency. So we can actually only get a really narrow range of frequencies that will give us a positive gain, and a lot of frequencies that will give us basically a negative gain, which means the signal goes down. So if we look at the unity gain frequency for this particular filter, it looks like it's a little above 10 kilohertz. And I can't remember if I actually got a value on it or not. I will later, so won't worry about it at this point. But basically that's what the unity gain frequency tells us, is where we will get a positive gain and where we will get a decreasing gain. Not a negative signal, but a decreasing value, a negative dB. All right, so finding the unity gain frequency, we do the same thing we did before. So set the magnitude of the gain to 1 or 0 dB, and we, again, don't worry about the value of the negative or the positive. We don't worry about phase angles or anything. We just worry about the magnitude of the gain. And this time, omega R1C squared is going to be a lot less than 1, actually. So what we can do is we can actually eliminate that from the equation, which makes it much, much easier. So we can say that that's approximately equal to R2 over R1 times omega R1C over 1. And we can get rid of the R1s, and we end up with omega R2C equals 1, which basically solves for the unity gain frequency. So you will notice that for this circuit, we did use the break frequency as the capacitor and the resistor that are physically connected. And then for the unity gain frequency, we use the other resistor that's not physically connected to the capacitor. So the one thing that sometimes gets confusing for students is, when do you use R1, when do you use R2? And the best way to remember is, for break frequencies, the capacitor and resistor that are right there connected to each other, that's what they determine. And the other resistor determines the unity gain frequency. It is actually possible to make a differentiator without R1. It is possible to make an integrator without R2. All it means is that as the frequency goes really high or really low, the gain just increases and increases forever, which causes instability. So that's why we put the other resistor in there. So we have two frequencies that are also important for differentiators. Same thing. Differentiators don't give you the derivative above the break frequency. So for low-pass type integrators, it's below the break frequency. This is above the break frequency. So again, it's just kind of backwards from the previous one. And then signals below the unity gain frequency get attenuated versus increased. But they will still, you can still get the derivative of them. They just get smaller. So we have a general derivation formula if we were going to just calculate the derivative of signal going in, because pretty much any signal going in is some kind of function. So we can use the same values that we did before, kind of. Remember, with integrators, we had to integrate the signal, and we had minus 1 over R1C times the integral of the signal. And for differentiators, we have minus R2C times the derivative of the signal. That's the only difference, basically. And then you get different waveforms depending on what type of signal you use. So again, just like before, we'll look at two examples just to see how the waveforms are shaped. And as far as sine waves, we have, again, just a peak value of 1, 2 pi times 1,000 t volts, and we send it through this differentiator. So we can figure out the unity gain frequency, which we would like to know because we want to know if it increases or decreases in signal. And for this particular circuit, it's 10.61 kilohertz. So I actually did calculate it. This is the same one that we had the graph for. So if we go look at the graph, it is actually marked pretty reasonably on there in the right place. So the actual frequency that we're using is way down at 1 kilohertz. So we can look at the graph and say we expect a gain of minus 20.5 dB. which is basically 0.094 times the original signal, which is pretty small compared to what you put in. So we can go back and we can take our Vn as 1 sine omega t, and we can do the process mathematically and take V out as minus R2C times the derivative of the sine wave. And we take the omega out, because we always have to do that, and then minus R2C times omega times cosine omega t. And that means if we put the numbers in, we get minus 10 nanofarads times 1.5 K times 2 pi 1,000 times cosine 2 pi 1,000 T. And then if we put all those numbers together and we convert it back to a sine wave because we want to see how it compares to the input, we get 0.094 sine 2 pi 1,000 T minus 90, which is awesome. It actually comes out exactly like the Bode plot, which I would hope that it would, considering that it was simulated that way. And if we go through and actually run that waveform in LT Spice, we get the input being much, much bigger than the output. And when you look at it at this resolution, it looks like the output is like 0.1. But if you zoom in on it, it actually is exactly 0.094 volts at peak. So you actually do get exactly what you thought you would, which is nice. It's nice when things actually work reasonably well. For a second example, we'll look at a triangle wave going in. If you know the frequency of the triangle wave, you can actually figure out the slope of the line and all. If you don't, you can just say, okay, I know it's going to be a square wave and I don't know what it's exactly going to look like. Because I think in lab, you're asked for the shape, but you're not really asked for any other details other than that. But I still tell you how to figure it out if you needed to. So we have a 2 volt peak to peak, 1 kilohertz triangle wave. And we're going to calculate what V out would be. We just take minus R2C times the derivative of Vn, which is basically going to be minus 1.5 K times 10 nanofarads times whatever the slope of the line is, since this is just a triangle. And it is graphed below here, and you can see that it goes from -1 to 1 in half a millisecond. So that basically gives us the way to calculate the slope. We just take 2 over 0.5 milliseconds, and we get minus 0.06 volts. And what that means is that is the bottom part of the waveform, and then it's going to go up to that at the top. So to get the peak to peak, we actually have to double that. We get a 0.12 volt peak to peak inverted square wave is what we will get, since we got a negative value there. And we can run that through LT Spice, and you can see that the in is really big, the out is really, really small, and you can see it's also actually a little bit curved, just because it's got a little bit of error going to it, but that's okay. And we can't really tell that it's 0.12 volts peak to peak, but if we zoom in on that, we actually can. It's exactly 0.12 volts peak to peak, and that is how derivatives work.